Hello, everyone. My name is Liang Yan. I'm currently a software engineer from CoreWeave. This is a GPU cloud provider, startup model. Currently, we mostly provide GPU cloud to business customer there. We don't provide it to people development, but more like AI startup or other kind of AI companies there. So today I'm going to give you a topic about how to optimize AI cloud infrastructure, but not like from the AI model, but from a hardware perspective. So a little bit about myself here. Like I said, I live in Louisville, Kentucky, couple hours driving distance. So it's drivable to here. So that's why I've been keep here. This is my 7th time to the OLF. Always enjoyed being here. So I'm currently a performance engineer focused on the AI infrastructure and system machine learning. So I've been working on all Linux stuff, Linux kernel virtualization for over 10 years. I'm definitely open source enthusiast. Also quite enjoy ARM64 gig. All kinds of ARM64 board there. So yeah, let's back to the topic here. So I think we have been heard now AI is everywhere. We all hear people talking, hey, this is a model, that model. I have billions kind of parameter, all this stuff. But I'm going to focus on the AI infrastructure because when we kind of see this kind of news everywhere. This company spend billions of dollars to their data center. That company, like XAI, bought hundreds of thousands of GPUs there, which also cost $1 billion there. So it seems $1 billion is kind of a startup for the AI infrastructure, AI cloud. So yeah, so I think first I'll introduce a little bit about what would be AI infrastructure, what it looks like, and why we need them. And then step further, we'll see like what makes AI infrastructure special, and when we want to optimize it, what should we focus on? Last part is from the machine learning perspective, mostly from the system machine learning perspective. We'll see how we could take full advantage of your AI infrastructure because we spend kind of $1 billion there. We definitely don't want to waste the hardware there. And we'll just see how that could work. We'll also share some observation and some tips lessons we learned during the process. So I think let's start from the AI cloud and AI infrastructure side. So now it's everywhere, but people may ask like, do they come from nowhere? What it would like before this AI generation? I would say actually it's not. Like it's actually been there for quite a while. Like before the now it's ChatGPT. Before ChatGPT, there's actually a long history back to 1940, 1950. It's all about machine learning. And back then, of course, there's no GPU. It's mostly CPU, and they call it HPC, high performance compute there. And if you see but they mostly from the big company, actually even company don't have this capital to do these things. It's mostly from like national lab or kind of a national research center or even kind of a medical or kind of this giant company. They're working on the HPC and they make it work. And then these days, suddenly comes to a cloud. And cloud is convenient. Cloud is easy and cheap there. So it's everywhere. Now, so when it comes to the AI, they kind of want an AI cloud there. So, but there's some basic difference. For HPC, like the high performance compute there, it's actually, it knows the task already. So the system there, they already know they know their system very well. They know the task very well. They just to try and make it efficient in this task. However, cloud is totally a different concept. It's like it's somewhere else. Like if you allocate, I'll provide you, and it's unlimited. So this is a totally different direction before the HPC and cloud. But the cloud, because using all the virtualization or containerization, it makes it quite cheap and easy to management. They're just about convenient, make it quite popular. So people thinking like now today, so we need this high compute, and we already have the compute. So why don't we have this AI cloud? And based on that, it comes to AI cloud, and then also comes with the AI infrastructure. But what does AI cloud really looks like? So if thinking the traditional HPC, it's mostly, you could see, it's a bunch of servers there, and they run the like Slurm today. It's kind of a scheduler tools. Because they mostly care about how make a task run efficient, and that's all. So that's essential for AI, for machine learning. But that's not all. When you're looking at the cloud, it actually has more features there. It's like you could see it has all this infrastructure layer from like there's a data from the storage, and there is a resource, GPU, CPU, and all these hardware they could deployment, and after that you could put all the resource there, and then also it comes with the storage network. It also has like a DevOps kind of a function there. It could be monitor, and it could give you a lot of information. Also, there's some difference between the traditional cloud. It's like when we do the machine learning, we know there's a bunch of data there. So you see the left side, it's actually quite a bit about on the data set. And also, if you look at the center side, because they needed to do all kinds of the HPC kind of computer, high performance computer, high density computer there. So they actually needed some kind of a framework to do that, because they needed to, all these kind of AI machine learning, they high related to mathematics there. And if we programming there, we kind of need we definitely don't want to do any kind of a mathematical equation there. So it comes all this kind of a framework, distributed training. There's also PyTorch, Fast AI there, and this is specifically for the AI. But now we kind of merge them together. So we come to this AI compute. From hardware side, yes, we definitely want a special AI cloud outside. It could have everything there. It could easily maintain, manage the hardware. You could get the data, training, and then share the API to your customer, and all in one place, in one data center. But how does the AI model today, like how does the AI model also kind of need an AI infrastructure based on that? Do they need to think about AI infrastructure? The question is actually yes. You're looking here. This is a AI model tree here. You can see there's some pink. This is a tree here. There's some branches here. You can see there's some pink tree, and then the green and the gray kind of blue tree there. So this is actually how AI model developed these days. It uses some, because the large language model here, it's actually have different mode to do that. Like the left side, if you see the pink, there's a encode only mode. There's also decode only mode, and there's also the encode and decode mode. We can clearly see that the blue tree is quite survived there. That's actually because it's easy to deploy it it's actually from the infrastructure. It's easy to deployment there. It could easily to scale to a whole infrastructure. That could make it, that's becoming more and more popular there. So it comes to a lot of other models there based on this decode-only pattern. So yeah, this is like before 2020, it's more like traditional machine learning or the very simple neural network learning there. The data set is relatively small. It's like it's only like 10 billion parameters there. The model size is also small. It's 1 gigabyte there, and the professor in the school could do that, could develop that. They could only spend like 100K money there, buy a few GPU node. They could totally develop that. And their focus is how to get a better algorithm. But after that, OpenAI, the OpenAI scaling law there, they found that if you get more data set there, and you put more parameters to your model, you could get a better performance, a better model there. So suddenly all these kind of AI startup, AI corp, they are trying to expand. So now the data set is suddenly comes to the terabyte size, and the model is also comes to like 100 billion size. At this moment, they need like at least $100 million to go to a GPU cluster, at least multiple $1 million there. And now, because of all the data set, all the cluster get bigger, now direction becomes more focused on to process your data and how to do like the feature engineering and also like how to manage your data center. But that's only the beginning. After that, I think it's since from last year, late last year, early this year, and it gets even bigger. Like if you notice that like for Llama 3, Facebook, they have the Llama 3, and OpenAI, they have this GPT-3. But if you see all the news there, they said, hey, I only run this kind of training. It costs one time. It cost me like dozens of $1 million for one training. That's unbelievable. That's incredible there. Like that quite limited the people to do this kind of work. Academic, the university definitely couldn't afford it. Small company, they couldn't afford it either. So now it only limited to the giant AI company there, and like the AI, Meta, Google, all these kind of company. And also, it also changed the AI development there. That's why they come to the base model, and then the AI giant provide a base model, and then a medium or AI startup focus on the pre-train, and then get to the real domain model there, and then provide it to the customer. So yeah, from here we could see these days, it just getting insane. Like one H100 GPU there, they sold it like $30,000 for one GPU node. But the real material, bill of the material is only like $100 or $200. There's like 10 times profit for this kind of hardware. But does it really need? We don't know. But it becomes like it gives us idea. Like when we talk about AI, it means expensive, and it also means like we need a bigger infrastructure, an AI infrastructure there, and we need to spend tons of money there. And it also put the AI infrastructure to a very important place. Like, hey, we spend so much money there. How could you make sure we take full use of that? So to make sure this, we needed to kind of manage it well, and we needed to deploy all our stuff there quickly, and we also want to run the model efficiently, and then we could also provide to a production to get some profit revenue there quickly. So this is the I think this is the hope, but the reality is quite different. And even we spent like for the GPU there, it's so expensive. But expensive doesn't mean the quality. Actually, we saw when it comes to the AI infrastructure, we actually see more failures for this kind of a GPU server rather than the traditional CPU server there. So now we kind of know that we kind of want AI infrastructure. We want to add a specific infrastructure to do AI work. We need that, and it also already out there, like because if they have a good infrastructure, if your model could fit the infrastructure well, your model could get better. And we saw that evolution tree here. Like it's already get into this mode, the decoder only mode, because they could fit infrastructure well. So now we needed to go to see like what's the difference, what's the special for AI infrastructure, and how could we really make it worth it. So now so like I said, AI infrastructure is not comes from nowhere. We already know there's the HPC, the word, the traditional HPC word, and it's already been there for decades there, but they are using CPU. So now we actually, for this AI infrastructure, there's a big difference is that we have tons of GPU inside. And we also need to focus on the cluster. So we needed to make sure the GPU could communicate with other GPUs. The GPUs inside the same node or the GPUs across the node would be more efficient. So in that way, we need to make sure all the machine learning could training efficient, that all the data from the machine learning could communication with each node and each GPU more efficient. That's actually the strength of HPC before. We'll get there because a lot of this stuff is still from HPC, but just combined with, actually that's the difficult part, because most of the challenge is actually we try to combine HPC into cloud. For here is like we know the GPU add into the CPU, and if they want to communicate with each other in a cluster, they need some good network there. So there's actually two HPC network. There's two kinds of network there. One is called the InfiniBand. That's a totally different network infrastructure. The other one is actually Rocky. It's based on the Ethernet, and it's actually based on the UDP protocol. So you could still take the current network infrastructure and make it serve for your AI GPU. Of course, so like each node, they needed to connect to different switch. So this is the first thing we look to make sure how they could connect with each other. So we zoom in a little bit for this kind of AI infrastructure here. So this is one H100 server here. So if you see that, it's a giant monster. It has 8 GPU in a board there. And then that board connected to the server directly. So basically in this server, there's the normal traditional CPU, memory, storage, and then it with an extension board to connect 8 GPU. And from here, we see like because we are trying to optimize the infrastructure, so we definitely want to know the limitation of all this kind of stuff. So here is some kind of a memory bandwidth. Look for this one here. Now you can see why they want a GPU, why GPU is better for the AI. You see the speed here, like even for the bandwidth here. If we are using the traditional CPU, we are going to use the LPDDR5. This is the memory. And we are using the UPI. This is the CPU connected to CPU bus system. And there's also PCIe bus there, PCIe 5. But if you check the speed, it's only like 50, 40, 58 there. But if you check to the GPU, and even for the GPU connection, AV switch, NVLink. So yeah, a little bit extra information for here is that NVIDIA actually developed, we see there's 8 8 GPUs there. This 8 GPU is actually connected with each other using a different bus system. They call it NVLink. But still, you could see, like, if they write the copy data inside the GPU, it's terabyte per second. Even if they connect the GPU to GPU, it's still 408 megabytes. If you see, this would be like almost 10 times. The GPU system is 10 times faster than the traditional CPU performance there. So that's why they want the AI infrastructure. And even for the GPU, we zoom in a little bit, just go into the GPU itself. When we see the traditional CPU side, we know that there's a cache system, register, cache, memory, and all the storage. We know there's a hierarchy there. For the GPU, it actually has similar here. It has the global memory there. We already see it's kind of 2 terabyte. For this one, it has 3 terabyte per second. And it also has a cache system, the L2, and stick memory is also kind of there's also register file there. So you can see the speed is also like, hey, we already know that the GPU memory is fast, but the static memory, the cache inside the GPU, is even faster than the memory. It's like 4 times. The cache is 5 times above than the memory, and then the register is still like 3 times than the register, the cache there. So all this information, it causes to the memory wall there. Like when we do, if we want to really take full use of the GPU there, if we really want to make the all investment, AI infrastructure investment, the $1 billion they're worth, somehow it comes to this detail to make sure everything runs on the fastest path there. And this is the GPU connection. Like we see the board there. They have the NVLink, a specific board there. However, the speed is faster than the PCIe 5, but it's still not as fast as the GPU memory. So it gives us the idea, like if we could make all the machine learning running in one GPU, that's best. But if we couldn't, we want to limit it to the GPU to GPU. And even if we couldn't make that, we try to extend it to some system memory there. But with that, we needed to kind of connect to, so like here. Like if you see the other side, we needed to go through the PCIe side. So PCIe would be still a bottleneck here. The PCIe is 58, but the memory, is better than the 40 gigabyte that for the CPU side. So in this way, we still want to stick to the fast path here. And that's when it comes to the NVLink side. We could see it goes to the NVLink side. If we see there's a different generation, it has a different speed there. So because we are focused on H100, there's NVLink 4 and NVLink Sharp there for Sharp there. That's actually a difference between the network we are using, if you're using InfiniBand or if you're using the Rocky network side. And they also have some slight difference. Yes, goes a little bit slower is actually the PCIe bus there. So we still want to make sure it goes to the, so now it's actually, the speed is actually from 31 terabyte per second goes to the 3 terabyte per second, and it goes to like 500 gigabyte per second, goes to the 300 gigabyte per second there. But if that's still not enough, we still need to extend. So that goes to the PCIe. So it's like the speed here. So we want to go to the, now we needed to go to the PCIe. It's still 58. It's still better than the 40 and 51 there. So in that way, we kind of need some kind of a system configuration. We want to use the RDMA, remote DMA. We want to use some zero-phase system path there. We want to get the best performance. So here is an example. Like if you have the wrong configuration, it could go to really bad. It goes to the 85. It's only like 40% of the performance there. So all this information we should be keep in mind. We want to do kind of optimization for the AI infrastructure, for the AI model there. Yeah. So here we know that all these companies, they spend billions of dollars there, and they set up all the infrastructure. And we actually want to, during this infrastructure, they add a bunch of GPUs there, and a bunch of new network card there, the InfiniBand network card that. And we know that different devices, they have different hierarchy there. So to get the best performance, to get the best optimization, we kind of want to keep the rank there. So we want to, if possible, we want to run in one GPU. Even in the one GPU, we want them to run into the register or cache there. And if not, we go to the GPU cross the NVLink. If not, we use the GPU cross node. And if not, we go to the GPU goes to the CPU and goes to the storage side. Actually, all this information already being used on the machine learning platform. That goes to the optimization part. So like I said, I've been working on this specific optimization for the machine learning platform. We actually choose a benchmark called MMPerf here. It's kind of the most popular benchmark today. It's kind of the industry standard. A bunch of the company outside, like NVIDIA, AMD, Intel, Google, Microsoft, Amazon, they all kind of submit results for this kind of a benchmark. It's interesting, like there's inference side, there's an inference test, there's a training set there. So there's different model. We can see there's like a language processing model. There's image classification, object detection, recommendation, and even goes to the large language model, which is the most popular one from the ChatGPT. I think that's people start getting knowing it. But also there's some new one called the mixture of expert, like they put a multiple node in one model, so to try to see. So by looking at that, it can help to see the trends, like how the machine learning get involved. This is 4.1, but before that, it's all about, like, if you see the before that, it's actually all about the neural network, the CNN. But these days they started to add the new one, like the Llama, the mixture, and the GPT-2. They actually also kind of depreciated some RNN and ResNet, that model there. So you could see that these days people are liking the big model. They want to, and to support this big model, they need the AI infrastructure. And once the AI infrastructure, their hardware gets to the limitation, they needed to go back to kind of optimize the AI infrastructure. So, and when we do, because this is from the hardware side, we actually use some metric here to measure, like how should we do that, and how should we measure, like what we did there really helps there. So the left side is the training, for the training purpose. The right side is for the inference side. So for the training side, we actually measure the GPU utility. We see, like during all the process, how many GPU being used. And we also check the SM utility. This is from the CUDA layer. And there's also some tensor core utility. These three is mostly from a hardware perspective. But we actually see that it's not that efficient. It's not when we try to optimize our machine learning. And actually for like the model flops utilization is like during the whole training process, how efficient your model being used there. This is actually more helpful. And also there's hardware flops utilization. This is helpful, but this is a little bit tricky than the MFU there. And of course, there's time to train, like how many times we used to finish our model training there. Like I said, the current large language model, which need to spend like dozens of $1 million for one training there, they actually use like hundreds or thousands of GPU in the whole cluster. They need to train them like months, 3 months, 100 days there to finish the one training. So that makes it super expensive. And after that, it goes to the inference side. So inference side, the most straightforward case is our user case. Like when I open the ChatGPT, we type the code, we ask questions, and they send it to their server, their model, and then they give us the answers there. This is a typical inference process there. So at this time, we need to measure like, we definitely want it fast response, right? We don't want to like ask one question, we wait for half hours there just for waiting. That would be totally bad. That's actually the #1 metric we used when we measure our platform. And the other one is like time per output token. So it's like how big they could process. That's the like if you paste too much information to your ChatGPT, you actually could see the response that hey, I can't understand or I can't process that. You need to make it simpler. So this is the second metric. Others from hardware, we see the latency, the throughput, and the model. And also we needed to see like a model memory there, peak memory, how much memory they using during the whole one inquiry there. So like I said, like we discussed that all this information, all this optimization, it's relatively easier when it's only on one mode. But the whole infrastructure, the whole HPC things there is actually about cluster. It's actually about how running for the multiple nodes there, like hundreds, thousands of nodes there running together as one. So to do that, normally people need to do some kind of a splitting and parallelism here we call it. So for example, if the data set is too big, we just split the data set to different nodes. If the model is too big, we can like split the different layer, this layer to this GPU server, that layer to that one. And also maybe to make it more efficient, make the node waiting, because once we split different node, sometimes it may cause the stall. Like if they have the dependent, one node might need to the other node. So in that case, we introduce the pipeline. So we make it working one by one, so make it more efficient. Also, that need a lot of, like how to split them, how to make them efficient, that becomes a challenge. Luckily, there's some research already there for automatic parallelism there to do, like the mass TensorFlow, FlexFlow, one flow kind of thing. So this is all make it difficult. And we, like I said, we mostly focus on the platform side. So actually, luckily, there's already kind of a platform already doing this kind of work. So a very famous one is the Megatron LM. This is provided by NVIDIA. And it could already do all this kind of information for you. You have your data set ready. You have your model there. You can deploy it. You can set up a Megatron LM. And they could do all this kind of parallelism splitting for you. And also there's a deep speed there. It's from the Microsoft. And they actually also do some data parallelism for there. And Megatron Core, they kind of combine both Megatron LM and the deep speed there. And also, there's AI startup there today also doing this kind of stuff. The Hugging Face, which is quite a familiar one. famous one. They have the accelerator could do it for you if you have done any kind of training process. Causal AI is also quite a famous one. So all I test is that, for example, when we do that, our test, we really start up a cluster there, which have like 10, 12 nodes there. Yeah, because it's very expensive, we can't get a very big one. So we only focus like 12 nodes there, which has like 100 GPU servers there to do all this stuff. And we just set up a platform here, Megatron. We use Megatron LM, like Megatron LM or Deep Speed there. And then we just running that. While running that, we actually focused on, we're actually using all kind of observability, like the Prometheus, Grafana, and we track how the metric, we actually track the metric there to see how they really function, how they really working there. And if we see issues there, we fix them. And for inference side, there's also kind of a platform also side. The first one is 1030 LLM. It's also provided by NVIDIA. They also do all kinds of the optimization. But yeah, it's difficult to deploy and not good for the distributed situation. Like we can't do a very big model size there. So, and the GPU utilization is low. When we deal with a small batch size and sequence, it's like if we ask small questions there, we can see the GPU utilization is quite small. The other one is the VLM, and it has done a lot of optimization for this one. We also noticed that there's a deep speed. They also provide a very good framework for the inference. This is a little bit new for us. We're still working on that. So yes, so like I said, when we track, when we're doing this all kind of optimization, we actually track how the things, we track different metrics there to see how it works. So during our Megatron, during our test, when we're using the stable diffusion, we actually see that different batch size cause really different GPU utility there. That gives an idea that GPU utility is actually not a quite good metric there when we do optimization. Because there's some trick there. Like if you enable ASIC and GPU CUDA graph from the CUDA layer, you could see the GPU utility always 100%. But that's totally meaningless at that point. So we decide, after that, we decide to move to check the MFU, the model function utility there. So, and like I said, we test on, we have this different model here, the Llama 2. We also had the GPT-2. We also ran the Mistral 7x8B. This is the latest model, mixture of expert there. And also there's a new one from the MLPerf. It's actually the graphic neural network. That's really new. So we're using the Megatron LM. We could see we could get like 50% for the Llama 2. We could get 45 for GPT-2. Actually, for Mistral, we actually get the better performance from a different platform. Like we actually from the Causal AI there. It gives us like 54% of the MFU. By the way, it's actually like if you could maintain your MFU utility at like 0.5% there, it's already very good. So that could give you an idea how important when we do the AI infrastructure optimization. Even for this, there's so much work to do there. And for the inference side, we actually also tried a different optimization there. For example, we actually, to optimize the input, the prompt, I think ChatGPT, they call it prompt. And if we could compression the prompt that, so we can actually ask more prompt in one query there. So that could make it faster. And also there's the RAG called the retrieve augment retrieval argument, what does G mean? So that's basically like they will build the vector database for all the prompts that, like before you really do the query there, you actually go through a vector database there. They will translate your query prompt to a better one, which would fit to the model better. So they could give you a better results there. And also there's a model optimization. We could do, like said, if we could put everything in one GPU, if we could put all the stuff in the fast place, like the register and the cache and the GPU memory. So to do that, we actually do like a quantization. We try to compress the model. We even using some specification to use some mathematical method to make the model more smaller. And also we do some like the knowledge distillation there, and to do some droplet. Also from the architecture layer, from the model side, we tried a different attention method to try to, all the way we are doing here is like I said, we're trying to put everything to the fast memory side to make it movement fast to compute it faster. And yeah, during all these kind of steps, I would say it's, even we said that even this AI infrastructure, we spend millions, tons of money there, $1 billion there. It's actually more difficult, more painful than you think by comparing with many traditional data center there. And and we actually, during all this process, we see like now these days, like all the difficult part is to process the multi-node, multi-GPU keys. And quite interesting, a few years ago, I did a topic on the NVIDIA GTC. At that moment, they are still talking about the GPU virtualization. How do they put everything in one GPU? But now, even not to mention one GPU, if you even have the hundreds or thousands of GPUs, it's not big enough. But in that case, like if in a very smaller case, we actually see virtualization or GPU share is not that bad than bare metal. And then we see the model. Different model has different, so all this machine learning, they quite depend on the model, and the model, they have a very obvious pattern there. So which makes them, some model, the way you're dealing with one model may not be fit for the other model. And the RNN model there, it's really bad. We see it's quite sensitive with all your hardware, the disk I/O hardware there, which means like when we copy the data set from the CPU side, go to the GPU side, it's really slow. We can see the bottleneck there, very obvious. And then the GPU memory size, like I said there, is quite sensitive to the batch size. GPU size, it's much smaller. It's like the H100, it has like 80 gigabytes per second, but comparing the system memory, which has a terabyte already. And so we need to think about how to fit our model in like 80 gigabyte. Even for 8 GPU there, it's still 600 gigabyte memory there. So, and it's easily out of memory. So at that moment, you needed to change your batch size there. And we also tried like a mixed precision training. This is like if we data set, if the data format is 32 float, but if we could change it to 16, we could definitely make the size like 100% smaller. We kind of double size we like half size the data set. In other way, we kind of double size the memory size. However, it's not always true. It only help for some kind of the memory size there. Also, the 5 there, when we do the parallelism there, like even we, this is very compared to the 3. Like even we do all kinds of the parallelism there, the split, cross to the multi-node, we still don't have enough GPU. So at that moment, we need to add more nodes there, add more nodes there to make it work through. Or like we need to smaller the batch size, which will increase the training time. Like if we make the batch size smaller, like 50% smaller, we need the training time, we need to double the training time size there. That's unacceptable. That's because it's so expensive there. And also, we discussed all this kind of AI infrastructure, the hardware topo, all this kind of hierarchy there. So if we send the wrong information to the platform, it will cause the performance drop significantly. We could see like it even crossed the system. For example, when we set up, like when we're doing the GPU connect to GPU, it uses the NVLink there. So it actually needed to know all the hardware information. If we feed it a wrong information, we could see the performance immediately drop to 50%. And sometimes it even just cross the whole system. So in that moment, it gives the idea like it comes to give us the none. Like if we get a cluster there before running anything, we just run the communication test first. We run the MPI actually, Open MPI. This is from the HPC world, and then we run the NICO test. It's from NVLink. We make sure no matter how GPU or CPU good, we need to make sure the network side has already in the best state there, and this is really helpful. Yeah, the other side, we needed to monitor every time, like because it happened, it's so fragile there during all the time. We needed to do all the checkpoints. Like we needed to, every couple hours, we needed to save all the information to the disk in case it's broken, and it's easily broken. After that, we needed to restore from the last checkpoint and get back to it. So at that moment, we needed to monitor all this information. The metric, that's the metric we used before. We needed to make sure, yeah. We needed to see there's no big, if it's all one line there, that's good. But if we see there's some wave there, that's bad. That means something wrong. And sometimes we needed to stop the training manually. And we fix the issue and then get back to the training in case we waste more time there. So yeah, that's quite interesting. Like I said, even if we do one training, like the report, if they see the report from the Meta, Facebook about their training to Llama there, even the training, they spend like tens of millions of dollars there for the one training. They used 100 days there, over 100 days there for the training. Actually, the effective training time is only 20 or 30 days there. So if you see the efficiency, it's super slow. This is another kind of point goes to the AI infrastructure. We need to make sure they are very reliable. So yeah. And the other side, like the PCIe bandwidth, because when we run the heavy working load, we actually see the PCIe easily downgrade. So we know we so far it's PCIe 5, it's 126, 128, and there's 64 for the PCIe 4. Sometimes it will just drop to the lower bandwidth there. That's also very bad. So anyway, yeah. So I think it would only become more and more important for the whole AI infrastructure stuff. And people would more care about the scaling law, which is introduced by OpenAI from the 2020. And I think like people would be more careful about their training process to make sure to make them predictable, make it more efficient. And also heterogeneous memory, like because the GPU memory is really not enough. So we needed to include more kind of memory device there. In that way, we needed to think about all the architecture information we don't think before. Like NVLink C2C, it actually mitigated the memory between CPU system memory to the GPU memory. They they improved the performance by like 5 times there. And also the CXL, which is also popular, they also try to make make it all like they are trying to build a system memory pool there for all the training process. Unfortunately, CXL is too slow. They're mostly using for the inference side. NVLink C2C is actually for the training. And the last part, people are thinking to build one big computer now. I think it's kind of get back. Few years ago, Hewlett-Packard, while I was working at Hewlett-Packard, they come to the idea called the machine. So it's like they're using one giant centric machine to do all the stuff there. But there's really no customer care about it. There's no such workload there. However, things changed these days. There's the super pod, super rack, and super compute, depending on what you call it. NVIDIA comes with this all kind of super pod stuff. They try to put multiple nodes, like 256 GPUs in one node there. The current, the GB200, the Grace Hopper Blackwell 200 there, they all towards this way. Like if you could put everything in one computer, in one GPU, then you don't have too much thing to think about to optimize there. You don't need to think about the distributed machine learning there, or the distributed system there. So yeah, everyone's happy. But I think there will be a long way to do that. So yeah, I think that's all from my side. A bunch of stuff here. Hope you enjoyed. Hope you find anything interesting. Let me know if you have any questions, or feel free to reach me offline. Thank you.
Are there any questions?